Hi everyone, welcome to the 8th episode of Realistic Business Forecasting. This one's called Transformations. What I'm going to show you is how, if you have a relationship which is not linear, how you can convert it into one which is. Now, I need to warn you a bit here that this is going to be a bit of a messy podcast. It's quite complex. And because it is quite complex, I've actually made available for download the spreadsheet I used to undertake all the calculations you'll see here. So you can actually stop this video at any time and use the link there, and you'll be able to download the spreadsheet transformations.xlx. So what I'm going to do, I'm going to use data which I've used in the past for work. And I'm going to be looking at rail operator cause delays and the number of train miles run. The equivalent for roads is the speed of traffic and the number of vehicles on, say, the motorway. So let's start with the simple version. Here you can see it. It looks reasonably okay. And you can see the equation there. It's a nice, simple, or simplistic, linear equation. Now, let's look at two alternatives. I just used the function in Excel for trend lines, and I selected, first of all, a quadratic one, and you can see the equation at the top there. So it's x squared plus x plus a constant, and it does seem to fit pretty well. And I've also added an exponential function. And again, that also does seem to fit pretty well. Perhaps doesn't quite hit the high points as well as a quadratic, but let's not prejudge. So what do we actually mean by linear regression? Well, a linear function is just y equals something times x1 plus something else times x2 and so on. But with regression, the independent variables can be any function of x. It doesn't have to be a very standard linear equation. Let me explain. So the first one, the actual linear equation, is unsurprisingly linear. Who'd have thought it? That's a very simple equation. 0.0116 times x plus a constant is linear. But the quadratic is also linear because it's a constant plus or minus a function of x plus or minus another function of x. However, the third one, the exponential, is not linear. And to make it linear, we need to do something. We need to transform it, which is why I've called this podcast Transformations. So this is where I will probably lose 90% of my viewers, but here goes. We're going to use logarithms. Now, you probably remember these from school and you thought, oh, I'll never need to use logarithms again. But hey, guess what? Here they are. And I do use these quite a lot when I have to transform variables. Now, I'm going to try and make this as simple and as painless as possible. And we're only going to use two fairly simple equations to actually transform our function. The first one is that the logarithm of a times b is logarithm of a plus the logarithm of b. And the second equation states that the logarithm of the exponential of a is just a itself. So in other words, logarithms and exponentials are inverse functions of each other. I hope you're with me so far, because now we're actually going to do the algebra, which is generally not that difficult. Please believe me on that. So let's start with the original exponential function. There it is, y equals a constant times an exponential of that lot. So first of all, take logarithms of both sides. So we get log y equals logarithm of something times something. But you may remember from the first equation I brought up that the logarithm of something times something is the logarithm of something plus the logarithm of the other something. So we get the blue equation. Now let's look at this expression here, the logarithm of the exponential of something is just something. So our equation boils down to the logarithm of 1.1534 plus 0.0018 times x. The logarithm of 1.1534 is 0.1427. Just from Excel, you can do that, plus 0.0018 times x. So we now have a very simple linear equation. Logarithm of y equals 0.1427 times 0.0018 times x. See, it wasn't that painful, was it? Really? If you're not sure, take a look at it again. And again, you can play with the spreadsheet, which I've made available for download. So let's actually have a look at the headline results. What do we actually get? I've just picked 3 criteria here. So in terms of the adjusted R squared, the coefficient of determination, you can see that the quadratic is the best. Exponential is not too far behind. And linear is the least good. In terms of F value, which is the overall general fit of the regression, the exponential is best. And in terms of the significance of the coefficients, we can see that, well, again, we have a split result. The quadratic isn't particularly good for any of them. For variable 1, there's very little difference between the linear and the exponential. So it's not really clear at this stage which is providing us with the best result. So let's see what else we can do to actually find a winner from these 3. Well, let's look at the residuals first of all. And again, I've plotted all 3 on the line. What I've done is I've plotted these residuals in increasing order of delays per 1,000 train miles, which is the y variable. So what I wanted to look at here is whether or not the errors got worse as the y variable increased. And you can see, excuse me, that for all of these cases, once you get to about the value of 9, that's 9 minutes per 1,000 train miles, all of the regressions do deteriorate significantly. But 9 is a very high value. It is a typical value. Generally, the sort of numbers you expect to see in this industry are between 3 and 5. So over the range that we're genuinely interested in, which we would use for forecasting, all the relationships look pretty stable. But again, which one is the best? Now, in the last podcast, I introduced this concept of mean absolute deviations. And if we actually look at how far the errors do deviate from our y variable, we can see that the quadratic comes out best, closely followed by the exponential, and the linear is the least good of the 3. So from this, we will conclude that the quadratic function is the best. Or is it? Yes, there's a rub coming. Before I actually look at this rub, I just want to undertake to share the summary of the steps which we need to take. First of all, use a scatter diagram. As always, try and view the data. If you have to undertake any transformations, do so. If it looks like an exponential function is a good fit for the data, run the regressions, but when you actually come to compare the model and the actual values, do make sure that you convert log y back to y. So you'll have to take the exponential to revert back to y values. Step 4 is looking at the residuals and calculating the MADs. And then the 5th step is judging. There is a judgment call because there's rarely a clear winner, which is the best model overall for your data. So let's come back to this rub. So this quadratic did look pretty good, but it gave me cause for concern. If you look at the lower part of the range, we can see that as the amount of congestion on the railway network increases, the number of delays decreases, shown by this elliptical area here. And that actually worried me, and I thought, hold on, this does not fit with our hypothesis, which is that as congestion increases, delay should always increase. So I added a sixth step. I've said on more than one occasion that you need to have a hypothesis to actually, before you start undertaking your analysis. So once you've included judgment, was a quadratic the best value? And the answer is no, it wasn't, because of that problem with the decreasing delays as congestion increased at the lower end of the range. So on that basis, I would personally use the exponential, which fitted our hypothesis. I just want to show you one final example. You can see here that this is a cubic function. It's still linear because it's a function of x plus a function of x and so on. And this model actually looks really good. It has the highest coefficient of determination and it has the lowest deviation for its errors. That's great. However, if you actually look at the regression, and again, yet another reason never to use intercept and slope, look at all these p-values. They're dreadful. Not one of them. It's telling us that a coefficient is significantly different from 0 because they're all significantly greater than 0.05. So that's why it is really important to undertake all the tests. You should not stop partway through. You need to actually go through the full diagnosis. So let me just finish up with some lessons from the examples I've presented today. First of all, what shape of line best fits the data? You do have to use trial and error, but if you develop a series of trend lines, as I did at the beginning, it should give you some idea of which is going to be the best fit. Second, use transformations if necessary, such as logarithms to obtain a linear function. Third, you need to assess not only the coefficient of determination, the R squared, but also the significance of the coefficients and the deviation for the best fitting model. But also, you're going to need to make a judgment because it's unlikely that one of your models is going to be the absolute clear winner. And this judgment call means don't be blinded purely by the numbers. Actually sit back and actually think what the model is actually telling us. And let's say I pointed out that issue with the quadratic, which was not giving us sensible results. And to underline this point about undertaking all the tests, a complete hypothesis, that cubic variant I showed you in the previous couple of slides is a perfect example of why you need to carry out all the tests before you can come to any sort of conclusion. Well, I hope you're not too traumatized from logarithms and other things, and I do hope that was useful. So thank you for watching and listening, and do feel free to place any comments on the YouTube, and goodbye for now.